Yes, I'd like to begin by thanking the organizers for organizing this great conference and for inviting me to come speak. So today I want to talk about mark points in genus 2 and beyond. And the beyond sort of suggests that, well, what I wanted to suggest is that there are more miracles beyond what we see in genus 2. So the first example of a miracle in genus 2 is the fact that in H11 there's only one interesting Teichmuller curve. And I want to say that that sort of miracle, the miracle of the decagon, leads to miracles that we see in mark points and miracles that we see in higher genus strata of Abelian differentials. So what I mean by this will become clear throughout the talk. So let's begin, though, with a definition. So definition, and I should say throughout x omega is always going to be a translation surface. So a point P on a translation surface x omega is called periodic if, when you see the orbit closure of the marked translation surface, the dimension you get is the same as the dimension you get if you take the orbit closure of the unmarked translation surface. Okay, so we'll see an example in a second, or, well, I'll give an equivalent definition first. So equivalently, the map that forgets marked points from the orbit closure of the marked translation surface to the orbit closure of the unmarked translation surface is a finite map. Okay? So what does this mean? This means that we have some sort of translation surface, and if we mark a point, a priori we would expect to get one extra dimension, that we should be able to vary this point freely, but periodic means that we don't see that somehow the position of this point is constrained. And so the statement that the dimension of the marked orbit closure is the same as the unmarked can be seen to be equivalent to just having finite fibers. So in any translation surface down below, you only mark finitely many points up above when you take this orbit closure. OK, so that's a periodic point. So let's give some examples. So I'm going to draw a genus 2 surface, opposite sides identified. They always are. If I were to mark fixed points for the hyperelliptic involution, so fixed points for the hyperelliptic involution, or Weierstrass points, so these will be called WPs throughout the talk, are periodic. So why can you see that these points are periodic? An easy way to see that if I hand you a genus 2 translation surface and we mark a Weierstrass point, then if you hit this translation surface with an element of GL2, the new surface is still genus 2, and the point that you've marked is still a Weierstrass point. In any fiber over any genus 2 surface, there are at most, in this picture, 5 Weierstrass points plus the 1 at the 0. And finiteness of the fibers is the same thing as being a periodic point. So Weierstrass points provide us with our first example of periodic points. Another example is rational points on the square torus. So by rational points, I mean I'm drawing a square torus like this, vertical length 1, horizontal length 1. Any point there with rational coordinates will be a periodic point. Okay, so more generally, from this you can see that on torus covers, it is possible to classify all periodic points. Just as a simple example, if you have a square-tiled surface, what are your periodic points going to be? They're going to be precisely the preimages of your rational points on the square torus. Okay. Periodic points pull back under branch covers to periodic points. Any questions about this so far? Yes?
Sorry. defining the translation surface, are we allowed to cut the surface apart and paste it on the other side?
Yeah. So you're always allowed to do that,
So
right?
we can cut the irrational part and paste it to the left side. Then the rational becomes irrational, and like that.
Wow. So I don't believe that should happen when you have a squared torus. So in particular, if you pass to the universal cover, so on the universal cover, this looks like R2 mod Z2. I'm saying literally take any point which is going to belong to, so your periodic points are exactly going to be the image of Q2 mod Z2. Pardon?
That's like doing an irrational shift on the universal cover.
Sorry?
That's like doing an irrational shift on the universal cover.
Mark point 0. You can't move the mark.
Yeah. Thanks.
Okay.
There's a mark point at 0. Right.
The square torus is the mark.
Right. So you're branched over, say, this point. Thanks.
Thank you.
All right. Other questions? If not, then with these two examples in hand, so, does the backboard not go up? That's too bad. All right. Hopefully you wrote that and remember it. If you don't, then just ask me. Yeah. All right. Erasers over here. Yeah, so the question I want to ask, since example 2 sort of suggests that if we have a torus cover, we know what all the periodic points are. The question I want to ask is, what can we say about interesting mark points, in other words, about periodic points, on genus 2 translation surfaces? So the theorem I want to talk about is the following. It's if x omega is a primitive genus 2 translation surface, then the periodic points are zeros. We definitely mark zeros, finitely many in each fiber. Weierstrass points. We just convinced ourselves that Weierstrass points are always periodic points. And there's only one more example. It's the 2 golden points on the golden eigenform locus, omega E5. Okay, so I owe you an explanation of what this is. So at the beginning, I'm just going to say what the golden eigenform locus is, and that will also give you probably the shortest proof of this theorem that you could imagine. So definition, omega E5 is the locus in H11 containing the decagon. Okay? And that's all that we'll need to know about it. And so the first miracle that I want to suggest related to the miracle of the decagon is the fact that if you have a primitive genus 2 translation surface.
Wait, hold on.
Yeah.
Confusing definition, right? Because the asymptote of the decagon is a locus. What do you mean by a locus?
Let me say the eigenform locus. Decagon. So the decagon is some sort of, its orbit closure is a Teichmuller curve. That Teichmuller curve sits in some sort of 3 complex dimensional orbit closure. And that 3 complex dimensional orbit closure is exactly going to be the golden eigenform locus. Okay. And so this is sort of the miracle, the fact that you have just one interesting Teichmuller curve sitting inside of H11. That miracle is exactly what leads to this miracle that there's only one interesting marked point in genus 2. These two things are very related. So like I said, you could see this as a definition, but what I want to explain is that really this definition can also be seen in some sense as a proof of the previous claim. So these two things are related. Okay, so I don't want to define the golden point on the golden eigenform locus, but I will make some remarks. So remark 1 is that the golden point is periodic And that's work of Kumar and Mukamel. So, wow, yeah. So we do actually have this interesting periodic point. Wouldn't be so interesting, or wouldn't fit into this list if it weren't a periodic point, but it's due to them. And I'll say, remark 2, that the statement holds more generally for any quadratic differential or translation surface with dense GL2 orbit. And for abelian differentials, this is due to me. And for quadratic differentials, this is due to me with Alex Wright. So those are the 2 remarks that I want to make about this theorem. And now I want to suggest that there are 3 main ingredients for the proof of this theorem. So any questions about the statement of the theorem? Yeah?
I don't understand the remark. So what statement holds what?
Yeah, OK. So what I mean in particular is you throw me some sort of, say, translation surface. And you want to know what the periodic points are. So here's what they are. If it has a dense orbit closure, there's zeros, or if it's hyperelliptic, they're Weierstrass points. The golden points don't apply, so that's it. So in general, if I give you or if you give me a translation surface and you say, I know it has dense orbit, what are the periodic points? The answer is only the obvious stuff. And that holds both for translation surfaces, but also for half-translation surfaces. Dense in the component of the stratum containing the translation surface. Yeah, exactly.
But the genus is still true for this remark?
No, any genus. Any genus, so long as, well, I won't write it, but the word you should say is that so long as it's living inside of some sort of stratum of quadratic differentials, which is not rank 1. So if everything there has a orienting double cover, which is a torus cover, then you're sort of out of luck. The previous comments about periodic points on torus covers apply. But if you're not in one of those, I think it's 3 strata of quadratic differentials, then you basically have no periodic points generically. Yeah. Yeah, John.
So are you saying that there's some special points, for example, in the regular decagon?
No, there are no special points on the regular decagon. That would violate Martin's theorem. So I'm about to say what was known previously about this fact.
So the golden
Yeah.
points, OK, I'm confused here.
Yeah.
The golden points refers to what?
Yeah, so maybe I'll actually just draw a picture.
The golden eigenform locus, what are the golden points?
Yeah, so I'll just draw a picture then. So maybe remark 3. So here is an element. Phi will always be, for me here in this talk, the golden ratio. So here is some sort of surface in the decagon locus. Okay? And if you want to move it off the decagon locus, then what you do is you make this smaller. So we add minus t to this. You make this cylinder bigger. So you add plus t to this. And you make this final cylinder smaller. So you add minus t to that. And so the Weierstrass points are going to be these x's here. And the golden point is going to be the point which, after we've shifted by t, is going to lie at a height of phi t either above or below that Weierstrass point there. So that point and its friend under the hyperelliptic involution are going to be the 2 golden points on the golden eigenform locus. So it's sort of given explicitly as, here's a translation surface, here are these marked points. These marked points are special.
The decagon itself, it just coincides with the Weierstrass point?
Right, yeah, so phi times when t equals 0 is just 0, and so its height above this point is 0, so it coincides with that point on the decagon locus.
And part of the statement is that the only golden object is this locus omega E5, and there are now no other golden objects and no other golden points.
Yes,
Okay.
yes, exactly. Yep, so that's it. Just these 2 points on this specific translation surface happen to be special. But if you take these and you take the obvious examples that we talked about, you've seen everything. Those are all of the special points in genus 2. All right, so other questions before continuing? If not, then I want to say two things. So ingredients that go into this. So one is a result due to Martin Muller, who said the periodic points on genus 2 primitive Veitch surfaces are exactly the zeros and Weierstrass points. Okay, so John, when you were asking, are there special points on the decagon, I was assuming that you had this theorem in mind because this theorem, Martin's theorem, says that that can't happen. There are no special points on the decagon. And that's exactly what we see in this picture too. When t equals 0 and we hit the decagon locus, our points disappear. They coincide with our other special points. So this ingredient both solves the Veitch surface case, but it's also a crucial ingredient for coming up with what the mark points are when you're in eigenform loci. So it serves sort of two purposes in the proof. The other ingredient, actually maybe I'll call this C, due to McMullen, is that the decagon is the only nonarithmetic Teichmuller curve. Let me just write that out. Teichmuller curve in H11. And the third ingredient, due to Mirzakhani-Wright, which is all you need. These are the only three things you need for the proof. Is best seen with a picture. So I'll draw a picture, and then I'll say in words what the picture is supposed to suggest. So we fix some sort of affine invariant submanifold. Invariant submanifold M. And now we're going to take a path in that affine invariant submanifold. So what's the picture? Maybe I have this surface in H11, and I'm going to do our normal REL flow that we like, where we make this cylinder small by t, this cylinder big by t, this cylinder small by t. So this is sort of giving you a movie. And along the movie, what you sort of see is the middle cylinder becoming big, and the two cylinders on the end becoming smaller. So you sort of flow along this movie, and what happens is, suppose we have two marked periodic points, P and Q. They get carried along continuously to other periodic points. And what the theorem says is, suppose that along this path, at some point, say we reach here, say that the two periodic points, maybe I'll draw one as a circle, land directly on top of each other. Okay, so we had some sort of path. This is some path of translation surfaces in M, and they end up here at some sort of point in M. Really, you want to take the Mirzakhani-Wright partial compactification of M. You want to allow your points to end up there. But if you have two periodic points that vary continuously along this path that collide at some sort of point, call it x omega, then the conclusion is the GL2 orbit of x omega is not everything. In other words, if we're going along some path and all of a sudden we see two periodic points collide, then we know that that point where they collide is somehow special. Its orbit closure is not going to be a full orbit closure. Okay, so if we have some path, and at the end of the path, two periodic points have hit each other, this guy has a smaller orbit closure than the generic, say, element along the path. Okay, so to say it now in words, if we fix an affine invariant submanifold and a path, say xt omega t, converging to some x omega, and we have periodic points, continuously varying, but I won't write that down, not equal to each other along the path that coincide at x omega, then the orbit closure of x omega is not everything. Okay, so what's an example of this? Well, an example of this is exactly this picture here. So we have a periodic point, this golden point drawn in as a circle, and we have this Weierstrass point here. And as we flow from, say, t equals a half down to t equals 0, we have some path of translation surfaces. They're varying. And then at some moment, the circle intersects with the x. And that moment has to be exactly a point of the decagon locus by this theorem. If we're traveling along our affine invariant submanifold and all of a sudden two periodic points coincide, there's some sort of underlying reason for it. That underlying reason in this case is that you hit the decagon locus. So these are going to be the three ingredients of the proof. That you know the answer for what the periodic points are for Veitch surfaces, that the decagon is special, and that if you're wandering along a path and you see two periodic points hit each other, then there was a good reason for it. Okay, so any questions about these three ingredients? Yeah?
So in B, you said you weren't going to write it down, but the PT and the QT vary continuously. So are you also assuming that the closures of the marked surfaces with marking at PT and QT are also varying, are being kept the same or something like that? I mean, or for another.
Yeah. So I want this to be a path in the marked stratum. So if I have some sort of path here, xt omega t, this is some sort of path living inside of M. The condition about pt and qt is just that when I mark these 2 points, xt omega t, pt, qt is going to be in M with 2 marked points.
But then are you assuming that the orbit closure in the space of marked points also varies continuously as you move? So if you take the orbit closure of xt omega t, pt, qt,
yeah,
and you vary t,
mm-hmm.
is the orbit closure varying nicely also? Is that part of your assumption?
No, I don't want to make that part of the assumption.
So in particular, it could be like the cardinality of this finite cover could be going up with t or something.
That's right, yeah, yep. All right. Other questions about the 3 ingredients? All right. So now I want to show you why these 3 ingredients mean that you should believe this theorem up there. Okay. So what's the idea of the proof? The proof sketch. Okay. It's basically going to be to say that we can always see this picture in remark 3. That we can always, if we had a periodic point, then we could cook up some sort of degeneration, some sort of straight line in our affine invariant submanifold that moves that periodic point into a Weierstrass point without degenerating the underlying surface. If we can cook up some sort of straight line that moves the periodic point to a Weierstrass point, then B intervenes, and it says that our orbit closure has to contain some sort of Teichmuller curve. That basically boils down to saying that we are in this golden eigenform locus. So let me write some things more carefully. So first, we'll assume that x omega is not Veitch and does not have a dense orbit. So we get to do this, the Veitch part, by Martin's theorem. We get to do the dense orbit by remark 2. Okay? So we have some sort of element of the eigenform locus in H11. So in particular, by McMullen, if we say that M is the orbit closure, this is an eigenform locus in H11. Okay. All right. And so there's a great thing that McMullen proved about eigenform loci in H11. So given so M, there exists some sort of translation surface, maybe call it y eta, in M with the following property. So 1, so I'll draw it. It has 3 horizontal cylinders. And moreover, this REL deformation that we talked about, where we make the top cylinder smaller, let's say, the middle cylinder bigger, and the bottom cylinder smaller. So this picture where we flow, I'll call this flow eta sub t. Top gets small, middle gets big, bottom gets small. That this flow, so we have 3 cylinders, and the flow along eta t remains in M. Okay? So again, just to recap, by Martin's result in remark 2, we can assume we're in an eigenform locus. Once we're in an eigenform locus, results of Kurt say that we have some sort of translation surface here where we have 3 cylinders and where if we do this REL deformation, we remain inside our orbit closure. Okay? All right. So now, here's what I want to show. So this gives all of the ideas of the proof. And so we'll content ourselves, because it's a sketch, with the following claim. And I'll make one more assumption too. We'll call this cylinder B for top and for bottom. And we'll say that the height of T is less than the height of B, which is just convenient for what we're about to do. OK, so we have some explicit translation surface. And I want to show that there are no periodic points here using the 3 ingredients that we have up there. So we've moved our problem to this translation surface. And here's what I want to show. I want to say that there are no periodic points contained in the interior of the top cylinder. OK? So I just want to quickly sketch that out. So, and you might have guessed just by how the talk has proceeded so far, but this is mainly going to be a proof with lots of pictures and fewer words. So I think when I showed this proof to Alex Eskin, he suggested that this proof deserved to be a video or GIF or something instead of written out in words. So yeah, that's how it's going to be. So here's our proof of the claim. We have our surface. We mark our Weierstrass points. Not there. And we assume that we have some sort of periodic point P. So assume P is periodic. OK, now here's something which follows from Eskin-Mirzakhani-Mohammadi. So by Eskin-Mirzakhani-Mohammadi, P moves linearly along vertical lines. As we do this REL flow. So as we change this surface and we look at the position of P inside this top cylinder, because the orbit closure of x omega P is a linear submanifold, as we follow this path, our point is moving. Say it's moving in this direction at some speed. Okay? And so here's what we're going to do. So 1, suppose that P leaves the top cylinder before T reaches area 0. Okay, so our point, it's moving along some sort of straight line. It's moving along a straight vertical line. And let's assume, for instance, it's going so fast that before we can collapse the cylinder T, P has escaped. So now here's what we're going to do. So if that happens, so then we're going to shear. So we'll just apply 1T, 0, 1 to get to, well, let me draw this. You don't have to shear if you drew the picture the way that I drew it. So let me make it so it's obligatory to shear. So let's say that we started with this was our 3 horizontal cylinder picture. So if this is what you have, then you shear so that now the marked point lies directly above some sort of 0. Okay, so your surface now looks like something like this. Okay, so you shear so that the mark point is on this collision course with a 0. And now you flow under A to T. And because the mark point is moving so fast that it's going to leave T before T collapses, you're going to flow. And at some point, you're going to get a surface where the mark point has actually hit a 0. Okay? So if P is moving so fast that it escapes T when you do this rel flow, then what you do is you shear to put it on a collision course with a 0, and then you do the rel flow so that under the rel flow, P coincides with a 0 without degenerating the surface. Okay? So what does all this mean? Well, by B, we have some sort of path in an affine invariant submanifold, and we have moved our periodic point to another periodic point, to a 0. And so that means that by Mirzakhani-Wright, by B, the final surface has smaller orbit closure than M. And there's only one eigenform locus that contains a Veitch surface, which is what that has to be by Mirzakhani-Wright. So we have, by Kurt, that M is the golden eigenform locus. Okay? So that's in the case that we have this mark point and it's moving so fast that under this degeneration, it skips out of T. So now there's one more picture. So that was one case, and it uses this miracle about the decagon being this special orbit closure in H11. But the other case, where P is contained inside of this, this top cylinder for all times, that's going to use Martin's result. So it's a different sort of idea. So just to present the two, why these ingredients are all necessary ingredients. Let me keep the proof. Oh, man. Well, OK. So I'll try to do it all on this board to keep all panels of the proof, all ingredients, and the statement of the theorem. OK. So the final case to consider to illustrate why this is true is suppose P remains in T until T reaches area 0. So the first case was the periodic point moves very fast under rel. This is the periodic point moves very slowly under rel. It's trapped in that top cylinder for our rel deformation. And so what do? Well, so here is our picture again. Our point is here. And so we'll assume that we have sheared again so that this top cylinder contains some vertical saddle connection. And now what we're going to do is we're going to collapse all the way to the boundary. So we collapse. And on the boundary, what do we get? We get some sort of surface now sitting in H2. on the boundary, when we've collapsed a vertical cylinder, what we see is a Veitch surface in H2. In our periodic point, by virtue of having been trapped in this top cylinder, it goes to this line right here. But by Martin's result, so by, I think I called it A, yep, P must be a periodic point on the boundary, and hence a Weierstrass point or a 0. So that says this picture's no good. We have a 0 right here, or we have a Weierstrass point here. P had to land on one of them. Okay? So if P has to land on a Weierstrass point or a 0, that means, here are our Weierstrass points, that P can either be on this shaded line or on this dotted line. If when we collapse, it ends up at this shaded point or this X, that's the way it has to be. Okay? So let's just redraw our picture. Fine. P is over there. Now, what's the contradiction? Well, so now what you're going to do is shear our, let's illustrate this by putting P down here. Shear to perform one complete Dane twist in T. So now I'm going to take this picture. I'm going to apply a matrix 1T, 0, 1 to it. And I'm going to get back to some sort of picture. So after shearing, so maybe everything will fit over here. After shearing, because we performed one complete Dane twist, T still looks the same. The rest of the surface might look different. But I know two things. After the Dane twist, T looks the same, and P is not on one of these lines. When we've sheared, P is now somewhere here. So now we'll just collapse again. Same argument applies, and we can say, so then, and we reach a contradiction. Because when we collapse, this mark point is going to end up looking like this picture. It's not going to hit a Weierstrass point. Okay? So that's an idea of how to use degenerations to prove a result like this. You just have a little bit of extra flexibility. In this case, you just need a rel deformation, and you have these facts, a way of performing induction, an understanding of your Veitch surfaces, and an understanding of your special mark points in those Veitch surfaces. Then you have enough information to essentially, well, yeah, to literally work out what all of the periodic points are in all orbit closures that contain those surfaces you studied in the boundary. Okay? Yeah, go ahead.
How do you know that the limit on the limit surface is still periodic? I mean,
so that's also going to follow from Mirzakhani-Wright. So the boundary that and Alex constructed is going to be a boundary that works equally well for studying marked points as it does for studying unmarked translation surfaces. And one of the things that falls out from the results is that the image of periodic is periodic on the boundary. So yeah, other questions about the proof? OK. So that's this idea. I think that I will now leave the realm of genus 2 for the final miracle that I wanted to talk about. So before I touch the board, for a brief moment, there's going to be a somewhat complete proof of this fact on the board in these panels. All right. So that's at the very least the idea. Maybe I should make one remark, which is the proof that I've sketched here essentially shows if you have a periodic point, then you have to be sitting inside of the golden eigenform locus. And the reason that you're sitting inside of the golden eigenform locus is because that's precisely the locus in H11 that contains some interesting Teichmuller curve. But I did not prove the second part, which is that in the golden eigenform locus, the only interesting marked point is the golden point. The proof will be very similar to the arguments made here. There's nothing really so special about the case of the golden eigenform locus. But I think that all of the details, or rather all of the main ideas of this proof, are sort of contained in this proof sketch already. All right, so I won't show that the golden point is the only point in the golden eigenform locus. But if you want to know sort of a cartoon of why that's true, come talk to me afterwards. OK, so now, yeah, I want to mention orbit closures in H6. So this is the second part. And it gets at the heart of one reason why you might be interested in studying marked points. Marked points are great for solving the illumination problem, for saying something about finite blocking, for doing all kinds of billiard problems. That's one reason why you would care about marked points. But there's another reason, which is that you can probe what interesting orbit closures there are that are larger when you have an understanding of marked points. And that's what I want this second part to be a discussion of. So I want to start with the theorem. And this came out in a preprint that was released in January. So Eskin-McMullen-Mukamel-Wright. And they produced many interesting orbit closures in this paper, but in particular, they produced an example that's as follows. So they said there is an affine invariant submanifold, which we'll call M naught. It lives inside of H6, and it has the following property. One, the equations defining it in period coordinates have coefficients that are irrational. Okay, so it's not a rational affine invariant submanifold. And two, it is not a Teichmuller curve. Okay, so it's cut out by equations not defined over Q. It's not a Teichmuller curve. So this says it's non-arithmetic. This says it's big, living inside of H6.
It's not rank 1.
Pardon?
It's not rank 1.
Yeah, so this already says that it's not rank 1. So in H6, you have no rel. By not being right, a Teichmuller curve, you're not rank 1. OK, so there's an example in H6 of something non-arithmetic and big, which is surprising. These were conjectured, well, once upon a time, not to exist. So here is this interesting fact, or hopefully you'll find it interesting, strange. It's that M naught, the example that they found, is the only orbit closure in H6 satisfying conditions 1 and 2, that it's non-arithmetic and that it's big. Okay? And so this is the third and final miracle that I wanted to talk about. The first was the decagon. The decagon led us through this argument up here to the golden point. And now this golden point is going to be the miracle that explains this miracle, why there's only one non-arithmetic big orbit closure in H6. OK. So first I want to draw a picture of what this guy looks like. So I'll put the picture over here. So we're going to start. Sorry, did I hear a question? No? OK. So we're going to start by just drawing a picture of the golden eigenform locus with the golden point marked. So it looks something like this. We have, this is height, say, y1. This is y2. This is something like phi minus 1 of y2. And this is y1. And this has length x, and this has length phi x. Okay. So that's the golden eigenform locus. And so now here's how you go from the golden eigenform locus to this example that they found in H6. You put on a simple cylinder here and say that it has length x2. And you put on a simple cylinder here and you say that it has length x2. Maybe we'll call those x1. So I'll shade the simple cylinders. OK? So it's manifestly built from the golden eigenform locus. there are these two simple cylinders, and if you collapse them, you get down to the picture that we saw in genus 2. And if you can make that a proof, then you can prove this theorem. So I want to just really quickly sketch why this theorem is true and what the ingredients are. So before I do, any questions about this? OK. Right. So the two ingredients that we're going to have are the following ones. OK. So one, let's see, I used ingredients up to C there, so this ingredient will be D. So first ingredient says there is a translation surface x omega. So in particular, let M be an affine invariant submanifold satisfying 1 and 2. OK, so by the cylinder deformation theorem of Alex-Wright plus some geometry, you can say the following. There is a translation surface living inside your orbit closure with 4 horizontal cylinders, 2 of which contain simple vertical cylinders. OK, so if you want to know what this means in pictures, then you're in luck, because we already have a picture of what this is. What the first theorem says is just from sort of general arguments, you can build a translation surface that looks exactly like this, in the sense that there are 4 horizontal cylinders, just like there are here, and that 2 of those cylinders contain simple vertical cylinders, the shaded ones right here. So on a coarse level, just general cylinder deformation arguments already says that a picture like this exists in this orbit closure, whatever it is. Okay? And so this will actually be the same as B. It comes from the same boundary paper of Alex-Wright and Mari and Mirzakhani. So it says, collapsing the vertical cylinders produces a surface in the boundary with the following properties. 1, it has 4 horizontal cylinders whose lengths are not all rational multiples of each other. Each other. 2, the orbit closure of the boundary surface is 3-dimensional. And 4, there is a relative deformation supported on all cylinders. So there's a way of deforming this surface you get where you only change the heights of the horizontal cylinders and you preserve all absolute periods. Okay? And in fact, E is a consequence of the work of Mariam and Alex from D. Once you have D, E is actually automatic. If you read the paper.
Collapsing the vertical cylinders?
Yeah, so what I mean is, I have this picture over here. And so what you do is you take your 2 vertical cylinders and you just make them blink out of existence. So you just join this edge to that edge and make that cylinder go to area 0. Just collapse.
Does property 1 say 4 horizontal cylinders or 2?
It has 4 horizontal cylinders.
So you had 4 and then you collapsed 2 and you remain with 4?
Yeah, you have 4 and then you collapse 2 vertical cylinders. And it's like this picture over here. You had 1, 2, 3, 4. And now on the boundary, you have 1, 2, 3, 4 when you remember the position of the mark point. All right. So I guess I'll erase this middle board. So now, how are you done? You're basically done when you have all of this. So you, so here,
Collapse, sorry.
yeah, go ahead.
Collapse the vertical cylinders, you stay in it again because of Alex's stretch maps? Or, I mean,
Yeah, so the part of this that I swept under the rug, because I didn't want to define unparallel cylinders, is that these simple vertical cylinders form an M equivalence class. So I didn't want to define what that was, but in particular that means that you can collapse them simultaneously, stay in the affine invariant submanifold, and when you fully collapse them, you'll end up in the boundary.
And what does the number 3 mean, that there is a relative information supported?
Yeah, so again, we can, since we know that this is the only example, this is an instructive example to go back to. So what that means is that when we collapse these vertical cylinders, right, we have some way of raising or lowering the heights of all of these cylinders that preserves all absolute periods. So in this case, if we make this increase by 1, this decrease by 1, this increase by, say, phi minus 1, and make this, so say make this increase by a half and make this also increase by a half. That's a relative deformation where you've changed every single one of the heights of the horizontal cylinders. So that's a relative deformation. All absolute periods are fixed, and you've preserved, or rather you've changed the heights of every horizontal cylinder. So that's what condition 3 means. Okay, other questions? Okay. So here's how you're going to conclude. You're going to say x omega 7 horizontal saddle connections. Why? Because it was horizontally periodic, and everything in H6 that's horizontally periodic has 7 saddle connections. We collapse 2. So our boundary surface, let's give it some sort of name. This boundary surface is going to be called y eta. So y eta has 5. Okay, now if we say let G be the genus of y and S the number of singularities of eta, this tells us that 2G plus S minus 2 is equal to 5. Okay, that says that whatever we see on the boundary, it has to have the following property. GS can either be a genus 1 surface with 5 singularities. Yep. But that can't happen. That violates 1. We could be a genus 2 surface with 3 singularities. Or we could be a genus 3 surface with 1 singularity. This violates 3. Okay? So just by D and E, what we already have is that when we've done this collapse, so when we collapse, we arrive in either H2, 0, 0, so H2 with 2 mark points, or H1, 1, 0, just by purely formal computations. Okay? And now, because I'm running low on time, I'll just say this picturesquely or impressionistically that 2 implies that we are in H110 and that the orbit closure of y eta is a periodic point on an eigenform. So just using nothing but the cylinder deformation theorem and an understanding of the boundary, we found a way to degenerate our surface so that we're sort of exactly in the situation where we began, where we were trying to figure out what these periodic points were in these eigenform loci. And so, let's see, I guess I have to make this disappear. And so, what you can end up showing is the following, and this is the end of this proof sketch. So just from what we have here, so the boundary surface, the boundary translation surface will literally be this one that I drew a second ago, where this is, I'm not going to care about x and y's right now, so I'll just put in, well, maybe I should have, so 1 minus phi, and this is, let's say, phi. So, well, the lengths that I've written down are wrong, but the boundary translation surface is this picture that we've been drawing of the golden point on the golden eigenform locus. So what you have then is, just from general arguments, you know that if you have an affine invariant submanifold which is big and which is non-arithmetic, then there are two simple cylinders. You collapse them, and you get down to exactly this picture that we saw here. Now, if you collapse two simple cylinders and you get down to this picture that we see here, there are only a handful of ways that you can put simple cylinders back into this picture. So there is the way which leads us to the picture, which you can see in Alex, Kurt, Ronan, and Alex's paper. And there are two other ways to glue in cylinders. So for instance, maybe this way, which doesn't obviously lead to the picture that you saw in their paper. But the point is that you've controlled the geometry enough that you have three translation surfaces which you know have to be in this potential affine invariant submanifold. One, you know, actually gives you an interesting orbit closure, and the other two fail for simple reasons that you check by hand. But so the idea is, and the whole thrust of this talk, was that miracles beget more miracles. The miracle of the decagon begat the miracle of the golden point and the golden eigenform locus. And that uniqueness begat this uniqueness of this big non-arithmetic orbit closure in H6. And sort of the glue or the path that takes you from one miracle to the other are these degenerations. So this boundary of Alex and Mariam and coming up with clever degenerations is sort of the way to leverage your miracle to either rule out others or to show that there are only one. So that's all I have. Thank you for your attention.